All right, so we've been previously looking at some organic molecules and what happens when our oxygen atom bonds to a hydrocarbon. So we learned last time that a water molecule can react with a hydrocarbon and make this molecule that has an hydroxyl group or an OH bonded to it. And in a organic compound that has an OH bonded to it is called an alcohol, and we're going to look at that in a little bit more detail. But what we really wanted to pay attention to is why a compound with that OH, like that ethanol we looked at, had significantly higher melting points and boiling points than just the plain old ethane. So just the substance, just the carbon and the hydrogens. So we took a look at the bonds that were happening. And if I scroll up, we might be able to look at them. If we took a look at the fact that the ethane, the bond between the carbon and the hydrogen, the electrons are shared equally. But the bond between the oxygen and the carbon, and actually the bond between the oxygen and the hydrogen does the same thing, the electrons are not shared equally. So when we get this unequal sharing of electrons, it forms this polar bond, okay? And we learned that when the bonds or when the electrons are not shared equally, we got a partial positive atom involved and a partial negative atom involved. And that's because we remember that the electrons are negatively charged. So if they shift closer to one atom, they're pulling their negative charge with them. So the one atom ends up with more of the electrons. It's not a complete transfer like the ionic compound, but it's partial transfer. It's kind of partially transferred. So that means that they get partially charged. So these polar bonds are what is responsible for some changes in our properties. Oops, I did not mean to do that. And the reason why they're responsible for different properties is because they actually impact the intermolecular forces or those attractions between the molecules. Okay, so today we're going to talk about our types of intermolecular forces. And I'm going to apologize because my family is loud in the background, but that's just a reality right now. So I want you to remember that molecules of a substance are attracted to each other by intermolecular forces. Now, it can be confusing with another word I have on here a little bit in the third point, intramolecular. But I want you to remember that inter means between. So these are attractions between molecules. We learned that the more energy is needed to separate the molecules if there are more attractions. And today we're going to add if there's stronger attractions. Okay. And our atoms, and just a reminder that our atoms in a molecule are joined together by intramolecular bonds. So they mean within. So the covalent bond is something within the molecule. In the forces of attraction, the intermolecular forces are between molecules. Okay, so sometimes you will hear those terms, and that is the difference. Okay, so today I've added the fact that today I added this word stronger attractions. And I kind of mentioned in a previous lesson that there are different types of intermolecular forces. And these different types of intermolecular forces have different strengths. So some are stronger than others. And the type of intermolecular force a molecule can make depends on bond polarity. Depends on a couple other little things we're not going to really get into, but mostly it depends on if there is polarity involved in the molecule. All right, the first type of intermolecular force we're going to look at is the one we've kind of seen already. It's called a London dispersion force. All right, so And we usually for short form it to be LDF. And again, I'm sorry for the loudness in my family. So the London dispersion force is basically just a random attraction that occurs between all molecules. So every substance is going to make a London dispersion force. It's the one that we looked at before, where like the hydrogens are just gonna kind of be attracted to each other. Now, the couple things about London dispersion force is that it doesn't need a polar bond. And because of that, it's actually really, really weak. So all substances are going to make this London dispersion force. And again, no polar bond is needed, and it's very, very weak. So I would hit pause and copy this down. All right, the second type of these intermolecular forces we're going to look at is called a dipole force, or DDF. Now, a dipole force, it has to have polarity. So it needs to have polar bonds. What ends up happening is, if we look at the molecules I've drawn on the left, now this is a molecule we haven't seen before, but what we do know, and we do know, is that when a carbon and an oxygen bond together, they make a polar bond. So we have these two molecules here. They both have a carbon-oxygen bond, and they're both polar. So in fact, we might want to label that. I think my son's playing Fortnite in the next room. That's what you're hearing. So these are polar bonds. So because we have a polar bond, we end up with a slightly positively charged atom and a slightly negatively charged atom. And the dipole force that happens is an attraction between the slightly positive of one molecule and a slightly negatively charged spot of another molecule. So this oxygen ends up being attracted to this carbon because it's an attraction between this negative and this positive. It's kind of like oppositely charged magnets. Okay? And actually, I'm going to write that. It's kind of like, it is like oppositely charged magnets. They're attracted to each other. Now, because it's like a attraction between a positive and a negative, this is these dipole forces are actually they're pretty strong. Okay, so positive attracts negative. Ugh, I'll fix that. Come on. Ugh, whatever. Deleted half that word. All right, I will fix that. So dipole has to have a polar bond, because without the polar bond, you're not getting this polarity. You don't have a partial positive to attract to a partial negative. And that is exactly what is happening in a dipole. A partial positive of one attracts to a partial negative of another molecule. And because it's an attraction of opposite charges, it's a lot stronger than the London dispersion force. So make sure you've paused and you've copied this down. All right, last type of these intermolecular forces is one that is called a hydrogen bond, okay? So a hydrogen bond is kind of like a dipole, but it's a dipole that exists between very specific atoms. It's when a partially charged hydrogen attracts to a partially negatively charged fluorine, oxygen, or nitrogen. So if we look at these two alcohols here, what we're going to know is that this hydrogen is going to become partially positively charged, and this oxygen is going to become partially negatively charged. And that carbon is also going to have a little bit of a partial positive charge. We can write that in here. Okay, but it's not really important for a hydrogen bond. So the alcohol down here is going to be the same. It's going to be some partial charges again because we have some polar bonds existing. Ugh. So I am gonna highlight this carbon-oxygen bond because it is polar. So we have these polar bonds, and what happens is the hydrogen here ends up being attracted to that oxygen, and this hydrogen ends up being attracted to this oxygen. Now, for a hydrogen bond to happen, it has to be a hydrogen attracting to either a fluorine, an oxygen, or a nitrogen atom. So the way I like to remember it is, I don't know if you've ever seen the movie E.T. Phone Home. Phone Home. So that's my little analogy. So a hydrogen bond is an attraction, an intermolecular force. It's basically a dipole, but it only happens between a positively charged hydrogen and a slightly negatively charged fluorine or an oxygen or a nitrogen. Because it's an attraction between these two atoms that have really different electronegativity values, it's actually really, 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 really strong. So the hydrogen bond is the strongest, and then the dipole, and then the London dispersion. So you should realize that the hydrogen bond needs polarity. Because we need those partial charges to be existing between the hydrogen and the fluorine, oxygen, or nitrogen. I would hit pause and make sure you have this copied. So there are the relative strengths of the intermolecular forces we talked about. The London dispersion is the weakest, and then the dipole, and then the hydrogen bond. So depending on the types of bonds that happen within the molecule, so the intramolecular bond, so the covalent bond, if it's polar or nonpolar, helps us figure out what intermolecular forces the molecules will make. And those intermolecular forces, the strength of those determines the melting point and the boiling point of our substances. Now, the intermolecular forces also determines the solubility of the substance. My children are not listening when I ask them to be quiet. So the solubility of the substance is also determined by the intermolecular forces, and we will talk about that next time. So I'm going to have a task for you where you are going to look at a molecule and decide what types of intermolecular bonds are making. So does it have polar covalent or nonpolar covalent bonds? And then what kind of intermolecular force that molecule will make.